of you that are ready to go and paying attention up here, you will not have to watch the YouTube video later, although if you really want to review what we talked about, you can. So you can choose to write down whatever you want, knowing that it also will be on YouTube and available for you this afternoon. So, cool things about what you just saw. First of all, if you look up here at these different objects, there's a Post-it note, 8.5 by 11 sheet of paper, and a cap to a bottle or some other container. Does the same amount of rainfall in each area? What do you think? I got some no's. Why not? How could you measure the amount of rain that falls in the objects? How would you measure that? Yeah. Okay, maybe by weight, all right? So, falls on each of these objects, you weigh them before, and then you weigh them after. Maybe you could determine that. Which one do you think would have the most amount of rain falling on it? Okay, one with the biggest area. Which one has the biggest area? Paper does? You think the paper would win? The table will. Yeah. Table wins. The paper comes in close second. The reason why is the paper has the most area. So if we apply this to different objects, which of these two objects has the greatest area where rain can get in? Over here. So if this one has the greatest area where rain can come in, and we have these two objects outside, the rain comes in this one more. Right? So the rain comes in this one more. It comes in this one less. But the rain is coming down. Now the interesting thing is the rain comes down into each container. Which container will have more volume of rain? The big one or the small one? More volume of rain. Okay, right? So if we look at these two, you would expect this one to have a greater volume. Yeah?
I would think it would be the bigger one because it's going to be getting more rain and it still measures the volume just as much as that one because it would be wider instead of taller.
Okay? So this one will be wider than this one is taller. So we have a difference in how the rain is coming down as to which one would measure more volume. What do you think? Okay, so if it rains too much, the skull will get overfilled. But this one's catching more rain than this one. So wouldn't this one get overfilled first? If it's catching more rain? But it's much bigger. But it's got a much bigger area to catch the rain. Depends on how fast the rain's coming. But if the rain is coming just as fast in here as in here, this one's going to catch more water. This one's going to catch less water by volume. But what is going to stay the same as the rain is coming down? Yeah? Height of the water. The amount of water coming in is dependent on the area. But this one has a smaller area, so it gets less water. This one has a larger area, so it gets more water. So the height of it going up as it's raining, the height will be exactly the same. This is why you can use any object that's cylindrical, such as a bucket. That bucket right there, we put it outside, it's going to rain tonight. After it rains tonight, you take your ruler, stick it in. The height in inches or centimeters is the amount of rain. Guess what? If I stuck this outside, and this outside, and this outside, the height in all of these containers would be exactly the what? Exactly the same. This is really convenient. Now, in your lifetime, somebody might say, oh, I made the most ideal rain gauge in the world. Here it is. It only costs $99.95 or 10 payments of $19.95 each. Everybody in the world must use this rain gauge. Are they telling the truth? No, because guess what? These two are worth the same. This is a piece of trash. This is a very expensive category. They both will do the same thing. Now, if you really don't have any money and you have a dog your dog bowl, empty it out, put it outside. Sometimes dog bowls are shaped a little bit funny. It might not be as accurate as you want it to be, but anything that's cylindrical will work. What about this one? Will this one work, our Florence class? What's up with this one? It's got a wider area on the bottom, bigger area on the bottom than the top. So the proportion does not work. 2 inches on this, or 2 centimeters on this, again, the volume changes as you're going up. And because of that, if you have a certain amount of rain coming down here, a certain amount of rain coming down here, that's different volume. The height will increase dramatically as the rain comes down here. So this is why rain gauges have to be cylindrical in shape. And if they're cylindrical in shape, it doesn't matter how big or small that rain area is. Now, the cool thing about this is, if you have a rain gauge like this, very easy to use. Here it has inches laid out for you. Now, the funny thing about this rain gauge, let's see if I can show you what it looks like over here. Anyone have a ruler? Ruler? Got a ruler over there? Here's the rain gauge. Small ruler, big ruler, I don't care. Got a big ruler. All right. So here's the rain gauge. You'll notice here it has it in inches. Okay? That's how rain is commonly measured. So I'd like you to put up the ruler between the 1 and the 2 inches. Measure how many inches is it between 1 and 2? It's over 2 inches. 2 inches on this, is it really 2 inches? Oh. My goodness. What is wrong with this thing? Did they just mess up on this? It's a cheap toy? What in the world? 1 inch is equal to more than 2 inches. What in the world did they do? How weird. This is a rain gauge. I paid money for this. Not a lot, but I paid money for this. What in the world? Why is it measuring so weird? What's up with this? What do you notice at the top of this? Ah, a little lid. See this? A little funnel, a little spout. Does this spout have the same area as this graduated cylinder? No. So all you need to do, the reason they designed this way is so you can put this outside and look at it and see it from far away how many inches of rain came. 1 inch is really 2 inches on this scale. Now you may ask, well, why would they do that? Why don't they just keep an inch an inch? Well, if you worked as a farmer, and you're driving your truck and you're trying to see what field is getting the right amount of water, and you look at your rain gauge. If your rain gauge is only an inch and you're trying to figure out if it got a half an inch of rain, you would have to walk up to it and look at it and go, oh, it's half an inch. So what farmers do is they take a big funnel and they trap the rain that's going into that funnel, and then they have this rain gauge where 1 inch is from here to here. An inch is almost equal to a foot. Now, why would you do that? Well, if you look at this, here's our rain gauge. If the rain goes up to this level, this is 1 inch here, this is 2 inches here. How many inches of rain do they currently have at that level? Yeah, about 1.5. Can you see this from the back of the room? Yeah. Could you see this if you're driving by in your truck and you just looked over? Yeah. They also even put a little floating ball in here, like a red ball in here or something. So it's even easier to see. So they can drive by and go, boom, oh, that got some rain. Boom, that did not. You can write down the levels. Now, the really cool thing is, if you had this set up to a computer that measured this, you could have it automatically give water to the plants based on the rain they got or the rain they did not get. So they have just the right amount of rain to survive. Now, that's only one thing that a farmer does, but that's how you can design a rain gauge that works best for you. This one here, the reason it's bigger, slightly bigger. If they didn't have this little top on it, this would have to be an inch to an inch comparison. If they have this top on it, it doesn't look like a big top, but that top makes a huge difference. It doubles the height that the rain will get to. So this here is a way of measuring rain and why rain gauges, sometimes you look at it and you go, that's not an inch. That's like 10 inches. How can that be an inch? Well, it's because of the arrangement of where the water is falling, and it's based on the area of water that's going into that cylinder. Now, what you saw in this activity is that volume increases in a steady and predictable way to the height of the beaker. This is what is called a proportional relationship. Proportional says two variables are directly proportional when you can multiply the value of one by a constant to obtain the value of another. So in this case, the height of the beaker, okay, was proportional to the volume for each individual beaker. For this one, was the height proportional to the volume with this one? Your Florence class? Absolutely not. Okay, it did not work because it was not, again, a constant. Again, it was a curved surface. It didn't have a constant area like all of these do. So this is a proportional relationship. We're going to be using proportional relationships in our unit. I know we've used them before, so this isn't something new. Okay? The graph line and the math associated with the line represent an ideal. So your data may not have looked exactly in a straight line. It might have been a little bit off. That is what is called a measurement error. Now, measurement errors doesn't mean you did anything wrong. It's just there are fluctuations off of the ideal. The volume of rainfall increases regularly in relation to the height of the rainfall. The height of the rain collected in a rain gauge does not depend on the diameter of the container. Bucket, graduated cylinder, doesn't matter. Okay? The volume of the rain collected does depend on the diameter of the cylinder. So if we have this one and they're both sitting in the rain, and then I took them out of the rain, this one would have more volume, but they both would have the same height of water. Since they both have the same height, that's how people measure the rain based on height, not volume. Volume is not an accurate measurement of rainfall. Now, if meteorologists reported in terms of volume, they would need to use exactly the same rain gauge, exactly the same shape in order to compare measurements. And guess what? If we all tried to have exactly the same one, somebody would sell it to us for $1,000 and we'd all have to pay for it. And somebody would say, that's not a good idea. Or you'd have to buy something specifically made to gather rain. And it's a lot easier to go stick a bucket outside than to go buy something in the store just to measure rainfall. And in San Diego, it's even harder to do that because we get so little rainfall. We sometimes even have different devices to measure the rainfall that can measure it more precisely than just a single bucket outside. Now, there are countless examples of proportional relationships around us. For example, the number of steps in a staircase is proportional to the height of the staircase. 20 steps is equal to a certain height. The number of pages in a book is proportional to the thickness of the book. So if you're reading Hunger Games, the number of pages in that book is proportional to the thickness of the book. If you're reading Aragon, you'll notice it's a different thickness. The number of pages are different. The relationship between centimeters and inches is also proportional. Every inch is proportional to a certain number of centimeters. And that proportion is a constant relationship. Doesn't change. So volume is a proportional relationship. It's the area of the base times the height. In this case, it's pi r squared times the height. If you had a rectangular shape, you could do length times width times the height. Distance, speed times time is proportional. Inches is proportional to centimeters times 2.54. Molecules is proportional to moles times Avogadro's number, 6.02 times 10 to the 23rd. So this relationship depends on a constant number to give us molecules. This depends on a constant number to give us inches. These constant numbers are called proportionality constants. This is the number that relates two variables that are proportional to one another, and it is usually represented represented by a lowercase k, representing a proportionality constant. So the 2.54 was a proportionality constant between centimeters and inches. Now, we learned about these proportionality constants when we looked at molar mass. Okay? Molar mass is a proportionality constant that depends on the formula. So water's molar mass is 18.02. If we have a certain number of grams of water, we can determine the number of moles, and vice versa. Okay? We learned about proportions before. Okay? Proportions. You have one thing over another equals a proportion. So that proportionality constant is called lowercase k. Let's look and see how this plays a role in rainfall. So using what we know about proportions, okay, please figure out the volume of rain for a height of 10 centimeters in this rain gauge. Ready, set, go. You want to write down your answer, even if you can do it in your head. Write down your answer as evidence of, hey, I got this. Even if you don't know if it's right. Just write it down. We're going to be checking in about 10 seconds. All right, possible answers. First of all, raise your hand if you have an answer, period. Just hand up. I got an answer. I got an answer. I got an answer. You have your hand up, it means you are not doing the problem. You didn't do the problem. You got no answer whatsoever. You would put a 0 or a blank. All right? Keep your hands up if you want to tell me your answer. All right? Yes. 40 milliliters. That's an answer. Other answers? Anybody agree with Miss Emily? All right, got a majority of people that agree. 40 milliliters. Emily is absolutely correct. That is the correct answer. Nice job. Can you tell me how you did this? How you set it up, what you thought, anything like that? Yes, sir. 8 times 5? All right, cool. 8 times 5. All right, yeah. 8 over 2 over x equals over, 8 over 2 over x over 10, right? Did I say that right? All right, yeah. All right, put a 0 at the end of the 4, because you had that being a 4-to-1 ratio. All right, so as you can see, there are lots of ways of looking at proportions. Okay, absolutely. If I had to mathematically choose one that was something I've done before, we've done many, many times in this class already. Remember that this 8 is milliliters and this 2 is centimeters. That x is my unknown in milliliters. This is my 10 in centimeters. So we just have to make sure the units on the top and bottom match if we're using a proportional relationship, and then cross multiply. For those that you may not have gotten that same answer. 2x equals 80, and then x equals 40. All right, and that's milliliters because the units here are milliliters. And this 5, okay, is absolutely right. 8 times 5, where did the 5 come from? Well, the 5 came from the 10 to 2 relationship. Okay, the 10 to 2 relationship. So, those are all ways of interpreting this answer. Good job. We know about proportional relationships. Now, proportional relationships are also helpful when we're looking at snowfall. Okay, so we're going to look at the question, is 3 inches of snow the same as 3 inches of rain? So look at this. We're going to look at how water is present in equal volumes, how much water is present in equal volumes of snow and rain. To do this, we're going to look at this graph here. All right, if you look at this graph, what is on the y-axis of the graph? Mass. What is on the x-axis? Volume. All right, now the slope of this line is what over what? Okay, slope. Some people call it rise over run, to make it really simple. Rise is mass. The run is what? Volume. And mass over volume equals what? The density. So, which of these has the greatest slope? Rain, ice, or snow? Rain does. Which one has the least slope? Snow. Which one has the greatest density? Greatest density is rain. This value here is approximately 1 gram per milliliter. That's the density of water or the density of rain. You'll notice here, how do you get that? Well, if you choose 2 points, 10 to 15 is 5. 10 to 15 is 5 for both of these 2 points. The slope of the line, okay, it's a straight line going through 1, 1, and it goes through 0, 0. Now, one thing that's important about a proportional relationship, which I don't know if we mentioned clearly, is a proportional relationship always goes through 0, 0, the origin. So all of these relationships are proportional. Okay, for rain, this is the density of rain. For ice, the density happens to be 0.92 grams per milliliter. For snow, it happens to be 0.50 grams per milliliter. Snow has half the density of rain. So if you had a container that had water and ice, which one would float, the water or the ice? Ice floats, right? Put ice in your water, it floats. The reason it floats is because its density is less than liquid water. This is a very helpful thing for fish in lakes. If water was like every other material on Earth, it would first, its density of liquid water would be less than solid water. But because water molecules have an intermolecular attraction towards one of them, the oxygen side attracts the, what side of another water molecule? The hydrogen side. That attraction is called a what type of bond? A hydrogen bond. A hydrogen bond, which is called a what type of attraction between molecules? Tell the person next to you what an attraction between molecules is called. Between. Alright? So between molecules, it's called an intermolecular attraction. Intermolecular attraction. Now, it's called a hydrogen bond because this is a hydrogen, this is an oxygen. There's not a chemical bond between them, they're just sticking together. Now, the really cool thing about water is water's hydrogen bonds allow it to stick to itself. Because water is polar or non-polar? Polar. Because it's polar, it's got intermolecular attraction, it sticks to itself. The other thing that happens is when water freezes, the hydrogen bonds take over when water freezes, and it actually causes the water molecules, instead of being able to move past each other, they are in a rigid structure. And all the water molecules form a rigid, three-dimensional structure, which is known as ice. If water freezes and it's really far apart and it freezes in place, it forms a unique structure called a snowflake. That snowflake has half the density of liquid water. Ice has almost the density of liquid water. This is why ice floats on water, and this is why a lake freezes from the top down. So fish can continue to swim under the lake, and you can ice fish, or you can at least live through the winter. Snow also lands on top of ice. So if you're going skiing, okay, and you jump off of a jump, and you're lucky, there's snow there. But underneath the snow, there's what? There's ice. And if you're unlucky and you go skiing on a day where there's no more snow or Big Bear forgot to make the machines work that day, you hit ice. And ice and snow have a different density. This one has a much greater density, and this one does not. So this one's much nicer to hit, period. But ice is also a solid state, which isn't so nice to hit in general. So those are some things about density and mass and volume relationships with rainwater, ice, and snow. We know density is mass over volume. We also know we can solve it using mass equals density times volume. This density, guess what that density is called? It's called a proportionality constant. Every material has a particular density. That's its proportionality constant. If you want to know mass from volume, you use density. If you want to know volume from mass, you use density. The density doesn't change. Water's density will be approximately 1. Ice will be 0.92. Snow will be 0.5. Now, for any proportional relationship, the graph always passes through 0, 0. Scientists measure snowpack in terms of depth. So they will take a meter stick and put it into the ground, or much larger than a meter stick, and they'll measure the depth of the snowpack. Then you have to make conversions to determine the volume of water. So if you find the depth of a snowpack, the depth will be proportional to the volume. If you find the volume of snow, what can you convert that into? Density. Volume, you can convert it into what? Mass. Now, if you take snow and you melt it, will its mass change when it turns into water? No, the mass won't change. So you just say the mass of it, whatever it is, 100 grams, it melts, it's still going to be 100 grams. So will it have the same density? No, it will not have the same density. The density will, once it changes phases, it changes density to water. So, to look at this, I would like you to answer these two questions using the information we know about snow, ice, and water. So on number 1, we're going to take a vote. And number 2, I'll ask for just a few people to give me their thoughts or ideas. So in 1 minute, we'll take a vote. Ready, set, go. All right, on number 1, we've got a choice between snow and rain. So the question is, which has a greater volume? All those in favor of snow, raise your hand. 1, 2, 3. Okay, hands down. All those in favor of rain, raise your hand. 1, 2, 3. All right, non-voters don't exist, so the snow people won. Yeah? Would the volume be the same? Well, the thing that is the same is they have equal masses. So what you have to think about is equal masses. I don't know how many grams there are, but let's say there were 10 grams of snow and 10 grams of water. If we set up a proportion, we want to know the volume of the snow. We know that there are 0.5 grams of snow in 1 milliliter. And in water's case, it's a 1 gram per milliliter ratio. So is there an equal amount of volume because they're both the same chemical substance? Well, these are two different physical forms. This is snow, which is a solid, and this is water, which is a liquid. They do not have the same density, so if they have the same mass, we cross multiply 10 equals 0.5 times x. 10 divided by 0.5 equals 20 milliliters. In this case, 10 is to x as 1 is to 1, so x has to equal 10 milliliters. So snow is the correct answer because, as you could see, 20 milliliters of snow is equal to only 10 grams. So if you have the same mass, you're always going to have a larger volume of snow than water. What about ice and water? Which one would have a larger volume if you have the same mass of each? Ice. This is why when you put a soda, like a soda in the freezer, sometimes it explodes. Because the ice expands inside, it's a larger volume, and that causes it to break open. They redesigned some of the cans so they don't do it as much, but you can still break it open pretty easily. Now, what is the mass of 14 milliliters of rainwater? 14 milliliters, yeah? 14 grams. Yay! That's it. How do we get that? Okay, density, 1-to-1 ratio. That's it. So 1-to-1, 1 gram per 1 milliliter makes it pretty easy. So this is why rainwater is so much easier to measure than snow. They just let the snow melt and they can measure it much easier. You can even know the volume of snow based on the melted rainwater mass. You go backwards. Or the volume of rainwater. So this is why water is used so commonly for measurements. It's easy to measure. So now that we know about these proportional relationships, we're now going to look at weather forecasts and one of the details of weather forecasts. So if you look at these weather forecasts here, I want you to determine which city will be warmer and explain your thinking, and do you think it will rain or snow in either of the two cities? So please tell the person next to you what you think as quickly as you read it. Ready, set, go. All right, ladies and gentlemen. All right, which city will be warmer? Which city will be warmer? Raise your hand, tell me which city will be warmer. Russia, thank you for raising your hand. Russia, the entire Russia will be warmer? Just Moscow, all right? So Moscow is the city, Russia is the country. All right? Why Russia? Oh, sorry, Moscow, please. Why is it Moscow that's warmer in this particular situation? Yeah. Celsius and Fahrenheit, this little thing right here. All right, definitely different. 30 and 50, if I were to guess without knowing what C is or F is, 30 and 50, 50 seems larger, right? Okay. But since it's C, that makes a difference on the temperature gauge. Now, do you think it will rain or snow in either of the two cities? Okay, somebody says rain. What about snow? No snow? Why not any snow? Not cold enough. Not cold enough. So, you're telling me that 50 degrees Celsius isn't cold enough to be freezing cold? So if we walked outside today and it was 50 degrees Fahrenheit, it'd be freezing, right? You'd be like, oh, I'm freezing. Oh, it's so cold outside. It's not really freezing, right? Yeah, so when we talk about weather, we got to think about people's responses, but also about what we're actually measuring. Now, thermometers are used to measure temperature. Okay? What is a thermometer? What is a thermometer? How is it measured? Thermometers. Yeah, what do you think? Thermometers. Any ideas on thermometers? Yeah? What do you know about thermometers? They can have Celsius and Fahrenheit? Yeah. Okay, they have mercury in them. This reacts via heat. Okay? How many of you have ever used a digital thermometer before? Okay? Now, digital thermometers are a little different. You may be familiar with them. How do digital thermometers work? Mercury thermometers deal with a liquid and heat. How many of you have ever dealt with thermometers that have red stuff in it? Okay, the red stuff in there, that's alcohol. Mercury is a metal, a shiny metal. I might have to get out my mercury thermometer and show you what it looks like if you haven't seen it. It's not used as much in thermometers, however, it is still used occasionally. But liquids are often used in thermometers because of some of their properties. However, in a digital thermometer, what happens in a digital thermometer is there's a small battery in there. And that battery passes electricity through the metal part of the thermometer. The electrons, when it gets colder, the electrons move slower. So because the electrons move slower, it's able to give you a readout of how much the temperature changes those electrons. And that gives us a readout that's correlated to temperature. It's correlated to a liquid thermometer. So we're going to try to look at how liquid thermometers work, and we're going to create our own thermometer and see if we can get a more precise thermometer than a digital thermometer. Yes, sir? No, they don't use mercury. Mercury is a liquid under normal conditions, but it is a carcinogen, so they do not use it. The first people to discover mercury played with it, had fun with it, they both died, they all died of cancer. One reason why. But we also found a lot of other things. Marie Curie, the one that first used extensively used mercury for many different experiments. Because of some of those properties, they found that it can be hazardous to your health to breathe it in, breathe its fumes in to liquid. Now, temperature or measuring temperature, we're going to look at creating a thermometer and a temperature scale. You'll be able to describe how a thermometer works and explain the difference between the F and the C, Fahrenheit and Celsius temperature scales. So to do this, you're going to work in groups of 4 people. Okay? In your group of 4 people, you're going to be using a number of different beakers. They can be 250 milliliter beakers or larger ones. You're going to be using a thermometer that you're going to create. To create a thermometer, you're going to take a container like this, like a smell vial. You're going to take a rubber stopper with a 1 hole in it. You're going to place a straw inside of this, just like so. Does not have to go in very far. And then you're going to fill this with a chemical known as ethylene glycol. Ethylene glycol, it's green color because I added food coloring. It's also clear normally. So the food coloring will allow us to see this. You'll fill your bottle full of the ethylene glycol, and then you'll squeeze the top of this on top of it and squeeze down. If you do it right, the level of liquid will rise into the straw. Once you have it risen into the straw, then you're going to be putting this into a number of different solutions of different temperatures, and using a Sharpie marker, you're going to make your own thermometer. Ideally, you should be able to test an unknown solution and determine its temperature based on your thermometer. That's the ideal. You may or may not be able to test that. So you're going to make your own thermometer using ethylene glycol. Other materials you may need include the ice cream salt here, spoons, you need those. Test tube holders, you need those. Hot plates, there's hot water in the back, so you don't have to wait for it to heat up all day. There are beakers in the back over there for all the beakers you need. Any equipment you need out of the back you can use, just wash it and put it back when you're done with